In this video, we will work through some multiple choice questions from past AP Calculus exams, which pertain to first semester. In first semester, we learned about limits, derivative rules, and applications of derivatives. Problem number 1. At what value of x does the graph of y equals 1 over x squared minus 1 over x cubed have a point of inflection? Remember that a point of inflection is where a function changes concavity. For example, if a function changes from concave up to concave down, that will be at a point of inflection. A long time ago, we learned the graphical relationship between f, f prime, and f double prime. The part that's relevant to this problem is that we know a function will be concave up when the second derivative is positive, and concave down when the second derivative is negative. Therefore, the function will change concavity if f double prime changes signs. So our strategy will be to find the second derivative and then investigate where it changes signs. So let's rewrite this a little bit before we get started. 1 over x squared is the same thing as x to the negative 2 power, and 1 over x cubed is x to the negative 3 power. This will make it easier to apply the power rule. So let's take the first derivative, y prime. Using the power rule, we have negative 2x to the negative 3 power. Negative 3 times negative 1 is positive 3, so I have positive 3x to the negative 4 power. So there's your first derivative. How about the second derivative, y double prime? We'll do the power rule again. Negative 3 times negative 2 is positive 6. Positive 6x to the negative 4 power. Negative 4 times 3 is negative 12. Minus 12x to the negative 5 power. So this is the second derivative. I need to go ahead and rewrite this with positive exponents as I prepare to figure out where the sign changes are. So this will be 6 over x to the 4th power minus 12 over x to the 5th power. In order to find where y double prime changes signs, it will be useful to write this as a single fraction. So I need like denominators. If I multiply it by x over x, I will have like denominators. Both denominators are now x to the 5th power. So this means that y double prime is equal to 6x minus 12 over x to the 5th power. Y double prime can only change signs where y double prime is equal to 0 or where it is undefined. So, where is y double prime equal to 0 and where is y double prime undefined? Y double prime is this fraction right here. A fraction will only equal 0 when the numerator is equal to 0. So the second derivative will equal 0 when 6x minus 12 is equal to 0. Adding 12 to both sides and dividing by 6 gives me x is equal to 2. So this is one possible location of a sign change. Let's keep going. Where is y double prime undefined? Well, this fraction will be undefined wherever the denominator is equal to 0. But this means that x itself will equal 0. So this is another possible location of a sign change. We will figure out whether or not f double prime changes signs by making a sign chart. So I'm going to set up a number line and I'm going to put these values on it and we'll investigate from there. So here are the two critical values on this number line. Make sure you label your sign chart as F double prime. And let's see, how many rows do we need on this sign chart? We're going to need one row for the numerator and another row for the denominator. So those are the only factors that we have. Next, we need to figure out whether these factors are positive or negative in each interval. So at x equals 2, this first factor is equal to 0. 6 times 2 is 12, minus 12 is 0. If x is anything less than 2, I'm going to get a negative value. So for example, imagine that x was 1. This would be 6 minus 12, that's a negative number. If x is anything bigger than 2, I'm going to get a positive number. Of course, looking at x to the 5th power, if I put in a positive number, I'm going to get a positive result. So anything bigger than 0 will be positive. Anything less than 0 will be negative. But what about the overall sign of f double prime? In this first interval, we would have a negative divided by a negative. That would be a positive. In the middle interval, this is a negative divided by a positive, which is a negative. And in the final interval, we have a positive divided by a positive, which is a positive. So before I look to see where the sign changes are, we need to pay attention to whether or not either of these values are undefined for the original function, because you can't have a point of inflection if it's undefined. So if you look back at the original problem, okay, this is the original function y. X cannot be 0, right? Because you can't have 0 in the denominator. So I can forget about a 0 as a possible point of inflection because the function is not even defined at 0. So even though I do see a sign change right here, that's not a point of inflection. However, notice that f double prime goes from negative to positive at x equals 2. So there's your point of inflection. If this were a free response question, I would record my answer and justification like this. F of x has a point of inflection at x equals 2 because f double prime changes signs. However, this was a multiple choice question, so the answer is C. Problem number 2. What is the limit as x approaches 0 of this expression? Let's see what would happen if we tried to do direct substitution. If I let x equal 0, then I have e to the 0 power. And e to the 0 power is 1, then we have 1 minus 1, which is 0. So the numerator here would be 0. What if I let x be 0 in the denominator? Well, the tangent of 0 is also 0. We have learned that if direct substitution gives you 0 over 0, we are allowed to use something called L'Hopital's rule, which says that we can take the derivative of the numerator and the derivative of the denominator without changing the limit. So let's give that a shot. Taking the derivative of the numerator term by term, we first do the derivative of e to the 2x power. Taking the derivative of e is always fun because the derivative of e to the something is always still e to the something. If this is just x, I would be done. But because I have a function inside of a function, I need to use the chain rule and multiply by the derivative of this inner function. The derivative of 2x is 2, so I need to have that. The derivative of a constant is 0, so we're done. We've taken the derivative of the numerator. I think I'll put the 2 in front just for fun. We have memorized that the derivative of tangent is secant squared. So let's see what happens if we do direct substitution now. The 2 times x becomes 2 times 0, so this is e to the 0 power. Let me just go ahead and show this, I guess. So we'll have 2 e to the 2 times 0 power over secant squared 0. So this is e to the 0 power, which is 1, and 2 times 1 is 2. So what is secant of 0? Okay, off to the side, I'm going to work this out. Secant is the reciprocal of cosine. So I'm going to first ask myself, what is the cosine of 0? And on the unit circle, 0 is right here. The coordinates are 1, 0. Cosine is the x value. So cosine of 0 is 1. Secant is the reciprocal of cosine, so secant of 0 is also 1. If we square that, that's secant squared will be 1 squared, which is still 1. So we end up with 2 over 1, which is 2. So the answer is D. Number 3, for which pair of functions f of x and g of x below will the limit as x approaches infinity of f of x over g of x equal 0? Let's just try them out one by one. Before we go any further, remember that the acronym FEPL reminds us that as x approaches infinity, some expressions grow faster than others. Specifically, FEPL ranks the various types of functions in order from fastest growing to slowest growing. So looking at the expression that is first, e to the x power over x squared, we see that we have an exponential expression in the numerator. And then we have a polynomial expression in the denominator. However, according to FEPL, exponential expressions grow faster than polynomials. So even though the numerator and the denominator are both approaching infinity, because the numerator is growing faster than the numerator is getting bigger and bigger compared to the denominator. So therefore, the value of the fraction overall is getting bigger and bigger and bigger. So the value is approaching infinity. So in general, we would say that the limit does not exist. But certainly the limit is not 0. What about the next pair of functions, e to the x over natural log x? Well, the numerator is still this exponential function. The denominator is logarithmic. So we've got exponential versus logarithmic. Exponential is still growing faster. That is the same as before, and the limit is still approaching infinity, or does not exist. For the next pair of functions, we have natural log x over e to the x. So we have a logarithmic expression divided by an exponential expression. So the logarithmic expression is growing slower than the exponential. If the denominator is growing faster than the numerator as x approaches infinity, then the denominator is getting bigger and bigger compared to the numerator. In that case, the overall value of the fraction is getting closer and closer to 0. In other words, the limit is 0, and C is the answer. Number 4, let's find the limit as x approaches 0 of this function. First, let's see what would happen if we did direct substitution. At first, we get this, but we know that sine of 0 is 0, the cosine of 0 is 1, and sine of 0 again is 0. 0 squared is 0. So obviously in the numerator we have 0, and in the denominator we have 0. Because the numerator and denominator are both approaching 0, we are allowed to use L'Hopital's rule, which says that we can take the derivative of the numerator and denominator without changing the limit. Let's take the derivative of the numerator term by term. For the sine times cosine term, we're going to use the product rule. So we have the sine x and we have the cosine x. The first time through, we take the derivative of sine, which is cosine. And we leave the cosine alone. And we put a plus. Then we pass through again. The second time through, we leave the yellow function alone. And we take the derivative of the blue function. The derivative of cosine is negative sine. So I'm going to put sine x here, but because this is negative sine, I'm going to change this plus to a minus. So we have this. So that's it for the first term. We still have to take the derivative of sine x, which is cosine x. Let me scroll over a tiny bit. So we will have minus cosine x. And in the denominator, the derivative is 2x, just using the power rule. We can simplify this a tiny bit by writing cosine as cosine squared and sine times sine as sine squared. Let's see what would happen if we did direct substitution now. At first, we have this. But we know that cosine of 0 is 1, so we would have 1. Sine of 0 is 0, so that's 1 minus 0. Cosine of 0 is 1, so that's minus 1. 2 times 0 is 0. 1 minus 1 is 0, so we are still getting 0 over 0. Because the numerator and denominator are still approaching 0, we can use L'Hopital's rule again. So let's again take the derivative of the numerator and denominator and see what happens. First, I take the derivative of cosine squared. I'm using the chain rule. So the derivative of the outer function is 2 cosine x. But now I have to multiply by the derivative of the inner function. The derivative of cosine is negative sine. So I'm going to put sine x, and I will put the negative sign in the front. Similarly, when I take the derivative of negative sine squared x, the derivative of the outer function puts the 2 in the front, so I have minus 2 sine x. And then the derivative of the inner function, the derivative of sine x is cosine, so I have to multiply by cosine x. That brings me to the third term. The derivative of cosine is negative sine. So I'm going to put down sine x. But because it is negative sine, it's going to change the negative to a positive. So I will end up with plus sine x. The derivative of 2x is just 2. If I do direct substitution now, I get negative 2. Cosine of 0 is 1. So I'm going to just go ahead and put 1. Sine of 0 is 0. And I've got minus 2. Sine of 0 is 0. Cosine of 0 is 1. Plus sine of 0 is 0. So that's my numerator. In the denominator, I just have 2. Well, every term has a 0 in it. So that means that the numerator is going to be 0. So I have 0 over 2, which equals 0. So the answer is D. For number 5, we need to evaluate the limit of this expression as h approaches 0. But if we do direct substitution, if we put 0 in for h, then this is really just tangent of pi over 6. So we have tangent of pi over 6 minus tangent of pi over 6, which is 0. So the numerator is approaching 0. Obviously, if we let h be 0, then the denominator is also approaching 0. This means we can find the limit using L'Hopital's rule. L'Hopital's rule says we can take the derivative of the numerator and the derivative of the denominator without changing the limit. So let's take the derivative of the numerator term by term. The derivative of tangent is secant squared. So in the numerator we will have secant squared of pi over 6 plus h. The chain rule demands that we then multiply by the derivative of the inner function, but the derivative of pi over 6 plus h is just 1, so we don't actually have to do anything there. Be careful with the second term. Many students look at the tangent of pi over 6 and think, well, we have to do secant squared or something, but this entire term is just a constant. The tangent of pi over 6 is, what's that, 1 over radical 3 or radical 3 over 3? This is just a constant, so the derivative of this last term is 0, which we don't need to put. In the denominator, the derivative of h is just 1, so we really don't even have to write that down. So this is the new limit that we must evaluate. Let's do direct substitution. We get secant squared of pi over 6. Substituting 0 for h, the h is gone. Secant is the reciprocal of cosine. So maybe off to the side we should ask ourselves, what is the cosine of pi over 6? Hopefully you have memorized that the cosine of pi over 6 is radical 3 over 2. So therefore the secant of pi over 6 will be the reciprocal, which is 2 over radical 3. We are trying to find secant squared pi over 6. So if we take 2 over radical 3 and square the numerator and the denominator, we get 4 over 3. So the answer is B. Number 6 is very similar to number 5. If we do direct substitution and put in 0 for h, we are left with 5 times 1/2 to the 4th power minus 5 times 1/2 to the 4th power. Clearly that is 0, so the numerator is approaching 0. And if we substitute 0 for h in the denominator is also approaching 0, so that means we can use L'Hopital's rule. According to Mr. L'Hopital, we can take the derivative of the numerator and the denominator without changing the value of the limit. If I take the derivative of the denominator, I'm just going to get 1. So I'm not even going to bother writing that down. So taking the derivative of the numerator requires the chain rule. So taking the derivative of the outer function here, 4 times 5 is 20. So we have 20 times 1/2 plus h to the 3rd power. I would normally then multiply by the derivative of the inner function, but the derivative of 1/2 plus h is just 1, so we don't need to write that down. Please notice that this last term is a big fat constant. There are no variables here. So we don't need to simplify it to know that the derivative of a constant is 0. So we don't need to write anything else down. This is the new limit we must now evaluate. Doing direct substitution, we put 0 in for h, and we get 20 times 1/2 to the 3rd power. So 1 cubed is 1, and 2 cubed is 8. So that will give us 20 times 1 over 8, or simply 20 over 8. Dividing the numerator and the denominator by 4, we get 5 over 2. So the answer is A.